All right, so graphing in polar world. This is also not a normal X and Y axis. This is kind of a different world and a different mode of graphing. Also can be found on your calculator under the mode function. Polar is going to allow you to graph very sort of, I want to say, circular designs. I know that sounds like a weird description, but basically these are not going to be functions, guys. These are going to be beautiful little designs and flowers and hearts and things of that nature. And that's what this allows you to do. So what happens is instead of graphing with a normal XY like you would in function mode, that's not what we're up against. We are up against an R and a theta. The R, as you probably guessed, stands for your radius, and your theta is basically your angle. And that's sort of like when we did the unit circle, it's your angle measured from the east. I should say not the east, that's how I think about it, from the positive x-axis. Okay, so in other words, if I wanted to, if somebody was like, hey, you're in polar mode and I want you to graph 3, 120 degrees. So what that would mean is that I'm going to go out 3 radiuses. And if we were to look at a grid for polar, what it would look like is almost like a bullseye, because you're going to have all of these sort of concentric circles on it. And so you're going to find the circle with radius 3, which is 1, 2, 3. It's going to be this one. And you want to go to the angle 120, which would be about right here. And so 1, 2, 3. So this would be the coordinate 3, 120 degrees. Now another cool thing is you can actually graph with negative degrees, just like when we did the unit circle, because remember this is like 0. So 3, negative 120 would actually be like 120 in this direction, but I'm still on the 3rd ring, so it would be about right here. So that would be the point. In fact, I should color code. That one goes with that. I love highlighters. That one goes with that, okay? The other cool thing that people like or maybe don't like is that you can actually graph a negative radius as well. And that's kind of a weird concept. So let me show you what I mean by that. So let's say I wanted you to do negative 3, 120 degrees. So when you have a negative radius, it's actually best to go to your angle first, because a negative radius is almost like a negative vector, meaning that you need to go in the opposite direction. So what I do is I go to the 120 first, which we already kind of talked about, like this path would be 120 degrees. But a negative 3 means don't go out 3 circles this way, go out 3 circles in the opposite direction. So notice I did a complete 180 here. 1, 2, 3. So this point right here would be a negative radius and a positive 120 degrees. So just go to the angle first and then go out to your radius. All right, so what does this mean? It means that we can graph things that are more circular, because since we are on a circular grid, it tends to lend itself to being good for graphing circles or ellipses, or like I said, we're going to see all kinds of cool designs. And we're going to talk about different parent functions here. Real quick, I will give you some conversion formulas, because some people do want to know, like, okay, well, where would the point 3, 120 actually be if I was on an X and Y axis? So in other words, if I picked up an X and Y axis, right, and I laid it on top of this, then what would that point be right here? Well, you can probably guess. You're like, well, it's going to be some sort of a negative X, and there's going to be a positive Y just because of what quadrant it's in. But if you want to find exactly where it is, guys, it's super freaking easy. It's just like when we did vectors. You can imagine that that point is the top of a right triangle, and you can drop a triangle down. And we know that the radius is worth 3. And we know that from here to here is 120. So if you think about this being 180 degrees, then you know that this angle would actually be like a 60. And you could do some right triangle math and you can figure it out. So some people like to kind of go between the two worlds. These are the conversion formulas that I've always used. Like I like to use that X is equal to the R times the cosine of theta, because it would turn into like a SOHCAHTOA problem. These are actually going to feel like when we did vectors as well. y is actually equal to r times the sine of theta. And remember, theta, once again, guys, is you really do want to measure it from 0 over to where you lay. That way you don't have to think about negatives and positives, and you're going to get it right every time. The other thing that might be nice is converting the other way. Like, what if I have an xy and I want an r theta? Well, to do that, it's just Pythagorean theorem. Your r squared is going to be equal, excuse me. Let me undo that, Control Z. Your r squared is actually your x squared plus your y squared, because it's just a little right triangle right there, or you can just think of it as the square root of x squared plus y squared. And then what about theta? Well, theta, I like to use inverse tangent for theta in order to get that angle. Now, be really careful with your theta. You really need to look at your quadrant, like look at your location, because the calculator is not always going to know where you lie. It's just going to be able to give you an angle from the x-axis, and then you're going to have to look at your picture to figure out exactly where you are. So those are some conversion formulas that might come in handy. For instance, when you guys do get to calculus, these are the following things you're going to be asked to do. One of them might be something like to convert an equation, where it's like, hey, if I tell you that r is equal to the secant of theta, you may have to convert this into what's called rectangular mode or Cartesian mode. And all that means, guys, is it's function mode. It's what we've always used. It's going to be x's and y's instead of r's and thetas. And so to do that, what I usually do is, well, first of all, I would have to remember what secant is, which from back in when we studied trigonometry, remember that the secant is the reciprocal of cosine. And so I'm going to write that as r over cosine. Now, I'm not going to write it as 1 over cosine, because we can't make the assumption that we're on the unit circle. Remember, there's many concentric circles on these pictures. So secant is r over cosine, or in other words, r over x. So in fact, I think I want to make that jump too. So if you want to look back, we had a whole bunch of formulas for secant, cosecant, tangent, cotangent, and I would make that sort of a thing happen. And then from here, I would just try to figure out life. Like, what does this mean? What am I doing? Okay, so if secant is r over x, then what I could do is just try to maybe rearrange this. So rx is equal to r. Maybe I'll divide the r to this side. So x equals 1. So guess what? R equals secant theta actually just turned into x equals 1. Bizarre, right? Okay. So I guess if I were to graph this in the calculator, it would look like the graph of x equals 1. It would look like a horizontal line. So those are things that you can do with this. We can also do like a equation like x squared plus y squared equals 9. So what's cool about this is we already know what this looks like, because we just studied conics. So this is a circle with a radius of 3, right? We should all know that. But if we want to do this in polar mode, okay, if we want to do it in polar mode, then what we would do is use our formulas, and we would replace this with r's and thetas. Well, all of this above was equal to r squared. So r squared equals 9. So what does that mean? It means r equals 3. So what you could do, guys, is go to mode. You could go to change it to POL for polar. It depends on which calculator you have. Some of them literally say polar. Some will say POL. And then when you go to the y equals button, looky, it's already going to have the r set up, ready to go. And then you can just type in the 3, and you can hit graph, and you're going to see a circle with a radius of 3. So now we have an easy way to graph circles. So what are some other popular parent functions that go in polar mode? So there's going to be 4 that we're going to talk about. One of them is called a rose. Doesn't look like a rose, it just looks like a flower. But the equation of a rose has this parent function. Now, I'm actually using a cosine here, but y'all, this could be a cosine or sine, okay? Doesn't matter which of the two you use. But if this is what you are typing in, what's going to happen is the A and the B are very significant. The A right here is actually going to be sort of the length of the petal, that you see on your graph. And the B right here is going to tell you how many petals you see. Now, what's weird about it is if B is even, if it's an even number, then you actually need to, you need to double whatever is there, and that's how many petals you're going to have. So if B is even, you're going to have 2 B petals on your flower. If B is odd, then you're going to have that's very literal. You're going to have B petals on your graph. The other thing is with sine or cosine, I said it could be either one. This is actually going to help dictate if your petals lay on an axis or if they're in between. So as an example, let me show you. Like if somebody did this to me, like this, okay? 3 cosine, 3 theta. Well, what I would do is I would look at how many petals and I would look at cosine, because cosine typically starts on the positive x-axis. And what I would try to make happen is I would make 3 petals happen at a length of 3. So I'm guessing it's going to look something like this. And I don't have a calculator to check. I could plug in points to see if that's right, but that's my guess. Whereas if I did a sine graph, sine is usually in between. So I would think that a sine graph would be 3 petals, and maybe it's like more like this. That's my guess. Where it's, oops, that's up there. Where they're like right in between the quadrants. But like I said, I don't have a calculator to check it. I hope I'm not making a big fat liar out of myself, but that's typically what they look like. Grab a calculator, look for yourself, okay? But if that number was a 4 right here, or if that was a 4, then holy free holies, you're going to actually have 8 petals. So, and it's so hard to draw. It'd be like, anyway, 1, 2, 3. You'd have 4 down below and 4 above. I know I just drew one with 7, but you get the idea, I hope. Check it out, but that's a rose. Next parent function is a cardioid. They call it a cardioid because it looks like a heart. A cardioid has the parent function a plus or minus a cosine or sine of theta. And notice I have a and a, which means if you want it to be a heart or a cardioid, you need to have the same number in the front. And same thing as before, this a is going to serve as like the length of one of the radiuses, and the cosine is going to help dictate where this lies on the axis. So go ahead and just play with this and type in maybe 2 plus 2 cosine versus, 2 minus 2 cosine versus 2 plus 2 sine, and maybe 2 minus 2 sine. What this is going to do is show you which axis it'll lay on. It'll show you how to sort of flip it around. If you are taking BC calculus next year, kids, this is very important. There's a huge unit where you need to kind of know the shapes of these so that you can find the area of these shapes. And if you don't know what it looks like, it's going to make finding the area really hard if you cannot visualize it. So please check these out in the calculator and take notes on the difference of what these do. Now, what if A and A, what if these two numbers are not the same? So in other words, what if you have a parent function that's A plus or minus B cosine or sine of theta, meaning these are different numbers. Okay, well, what happens is your cardioid that typically, can look like this, it looks like a heart, it ends up either flattening out and looking kind of like what we called a dimpled, we don't call it a dimpled heart, we actually call this a limaçon. It's a French word, limaçon, and it's got a funky symbol there. In Texas, we say limacon. It's not a limacon, it's a limaçon. I'm going to try to say it like it's supposed to be said. But a limaçon is it's like a heart that's been like, stuff's happened. So it's either going to be flattened out. Sometimes it's like super flattened out to where you can't even tell that, there was anything happening there. And then sometimes you have a limaçon with a loop. And so what I want you guys to do is to figure out how to make these things happen, because it has to do with the A and the B, and which one is bigger. That's going to be a big deal when A is bigger than B or B is bigger than A. Make up numbers. It's also going to have to do with how far apart they are, meaning like if you're choosing numbers like 1 and 2 or if you're choosing numbers like 1 and 4. You know what I'm saying? Like the more or the bigger the difference in A and B, the bigger the difference in the graph it's going to make. So your job right now is to stop the video and play with that and take notes. What happens when you change those values up? So I said 4 parents. How many have I done? 1, 2, 3. Okay, I've done 3. So the last one is called a Limnus Gate. And a Limnus Gate looks like an infinity sign. And its parent function, legit, I never can remember. Hold on a second. It's like r squared equals, I'm pretty sure it's like a squared, and then once again sine or cosine of 2 theta. It's something like this. It's all wackadoo. But if you take the square root of this and give it a plus or minus, you can type it in the calculator and you should be looking at an infinity symbol. Yeah. Now, the only other thing that you might want to note is that this theta, it really is assumed, guys, that this is from a circle, like a unit circle. So you want to set your window between 0 and 2 pi, and you want to set your mode to radian. I probably should have said that sooner. So if you have not been getting good graphs, you might be in degree mode. And if you were in degree mode, I guess just make sure you're from 0 to 360 right here. So you'd have to go to your window to make changes to your theta. So hopefully, you know, ask a friend and you can figure that out, or ask me. But that's sort of how that works. So I just wanted you to play around a little bit with the different parent functions in polar mode. You know, you can make circles. You can make, if you view a circle as almost like, well, like we did earlier, r equals 3 or something like that. And I'm sure there's some nifty ways in polar to make ellipses and things. You can make spirals. There's really all kinds of things. So feel free to play around with your functions and see what kinds of things you can make, or Google some things like some cool polar functions and see what they do. But this is super powerful in like the graphics design world, because you know, how boring would all our graphics be if it was just like parabolas and functions, you know? But if you can make all kinds of cool stuff on a computer just using polar mode, then that's pretty cool. All right, that's all we got, and we'll talk to y'all later.